Hello, this is Marwan Omar, and my presentation today is on investigating the limitations of adversarial training for large language models in realistic spam filter deployment scenarios. So let's get started. The agenda here for us, we start with the introduction and then move on to the related work. Then from there, we will go and talk about the background and preliminaries, moving on to the methodology, and then later we'll talk about the results and the discussion, and then the evaluation metrics that we use for our study. And then we'll provide key insights and ideas from our study, and then we'll wrap up with conclusion and future research directions. So adversarial training in NLP tasks is enhancing model performance and security. This is what the research community is saying, that the adversarial training for NLP models or natural language processing or language models will enhance the performance and the security. So the NLP tasks that we have studied in the past: sentiment analysis, text classification, question answering, spam detection. So we have the reinforcement efficacy, discover vulnerabilities in these NLP models, resilience and robustness, and defensive mechanisms, and of course, enhancing the accuracy as well. So those were the benefits of the adversarial training from the perspective of the research community. So the research community is basically indicating that when we conduct adversarial training for NLP tasks, such as you mentioned, sentiment analysis, text classification, such as topic classification, question answering, etc., or document summarization, for example, we will gain all these benefits that we've mentioned. So reinforcement efficacy, we'll discover vulnerabilities, we'll gain resilience and robustness of the models, and it will act as a defense mechanism, and it will enhance the accuracy of the model. Integrating new training samples during the retraining is a challenge. So this is one of the limitations of adversarial retraining in realistic scenarios. And it provides only a temporary snapshot of a model's performance. So this is the challenge with adversarial training. So it doesn't ensure the consistent efficacy in real-world deployments, and then it provides only a temporary snapshot of our model's performance. So that means you don't know if the model will perform consistently after the adversarial training, after deployment or the deployment of the model. Here we are talking about the related work. And so some of the previous research studies in this space, they focus on creating adversarial samples or examples to strengthen spam detection models and incorporating these examples into the retraining process to boost model resilience. We take a static view of, and the studies take a static view of NLP models, neglecting their dynamic and evolving nature when exposed to real-world deployments. The other issue in the previous research studies is that NLP models may face previously unseen data with distributional differences from the original training data impacting their performance. Basically, what that means is that when we deploy these models into the real world, they might see data that they haven't seen before, which is very highly expected. Now we're moving on to talk about the background, the preliminaries for this research. to investigate the immediate and enduring effects of adversarial training or fortifying language models by integrating novel data sets, potentially encompassing out-of-distribution data and employing diverse learning algorithms. We explored the long-term implications of adversarial training, acknowledging recent advancements in this area. We addressed the potential temporal limitations of adversarial training when models are updated with non-adversarial data. Unlike prior studies focusing on immediate robustness against adversarial samples, our study emphasizes possible performance degradation over time. And then it highlights the importance of considering temporal evolution and distribution shifts in training data, a relatively unexplored perspective in current literature. So our research, again, it's on investigating the limitations of adversarial training for language models in realistic span filter deployment scenarios. So the primary task is to examine spam detection as a principal natural language task, adversarial training and examples, explanation of various notations and definitions, then performance disparities, formal definition of factors that may cause disparities in model performance after retraining. The objective from our study is to develop a spam detection classifier, example 0 for non-spam and 1 for spam. The learning algorithms that we use are BERT and Roberta to implement the spam classifier. And then evaluation metrics, we will introduce the metrics that are used to evaluate the efficiency and the accuracy of NLP models. For the spam detection in textual input, so we have denotation. So an adversarial instance denotes an input intentionally designed to mislead an NLP system, which may result in inaccurate forecasts. Adversarial example X can be obtained by solving the following optimization problem, as mentioned here. Adversarial examples: for the assessment method, we utilize text attack queries to target the model. The algorithm phases: phase 1, rank words in sentences based on their relevance to prediction output. Phase 2, we use a word transformer to replace pivotal words with semantically similar alternatives to mislead the target model, ensuring minimal changes. And then validation checks maintain part of speech uniformity and assess semantic resemblance during word replacement. And the metrics that we use are accuracy, effectiveness, attack success rate. Background and preliminaries again continued here for the adversarial training. So adversarial training involves generating adversarial examples or samples by applying perturbations to textual data. These samples enhance the training data set and they improve the robustness of NLP spam classifiers against adversarial attacks. For the model adaptation, the primary goal is to ensure robustness against changes in the model. And the objective is to improve the ability to adapt to evolving data distributions. For the method, we incorporate additional samples and fine-tune models to enhance the resilience against adversarial attacks. For the proposed solution, we implement model adaptation by retraining models with new datasets. Challenge identified here is that NLP models performance can decline with changes in data distribution, leading to inaccurate predictions in spam detection. For the baseline model, the initial setup and performance assessment was explained. For the adversarial examples, we test the model vulnerability causing accuracy decline, and then for adversarial training, defensive, which considered again a defensive strategy to improve robustness. We have the concept drift, which analyze data distribution changes affecting the model. Retraining, so adapt the model to new data patterns with adversarial examples. Effectiveness check, validate the ongoing success of adversarial retraining. We start with a pre-trained model, then we have adversarial examples, which will have a high misclassification when we attack the model, and then we have adversarial training, the misclassification will go down. Then we have the concept drift, which means that the classification will go down as well again. For the methodology, we have our experimental framework overview. So the objective is to evaluate the influence of adversarial examples. We have selected models, BERT, CNERG, and Roberta. The key insights here for the resilience of language models, effectiveness of adversarial training, comprehensive evaluation. The data sets are tweet-eval benchmark data set, encompass 3 distinct data sets, Enron, spam, and link spam. So these are the data sets that we used. For the training algorithm, we projected gradient. The training algorithm is PGD, projected gradient descent algorithm for training a spam classifier. For the adversarial attack generation, we adopted the text attack framework to generate those adversarial examples. As far as the implementation, we have the input features X, which are multiplied by weight matrix W and augmented with a bias vector B. We use the softmax activation function and apply it to obtain class probabilities. Softmax cross entropy cost function is used to assess the predictive performance. For the adversarial attack generation, and that included both original data and adversarial examples. In the training process, adversarial examples collected from the Enron spam dataset. We utilize adversarial examples to again deceive the spam filter, to attack the spam filter. Data shift and relevant inquiries. Effectiveness of adversarial training is confined to the existing static dataset. Adversarial examples are less applicable to other datasets. So we have the real-world deployment challenges. So NLP systems encounter new out-of-distribution data. So that means they might encounter new data, even though we train our model with spam dataset. That doesn't mean that the model will experience the exact same data. It might see data that it hasn't seen in the training. So that's one of the challenges, which may lead to shift and temporal changes, resulting again in concept drift. For the concept drift, unforeseen changes in the statistical properties of the target variable indicates potential performance deterioration over time, and NLP models are likely to face decreased performance with new data in real-world environments or scenarios. We're moving on now to talk about the results. So we validated the limited impact of adversarial training on spam classification models due to data shift. With the experimental procedure we conducted across diverse datasets, employed different model architectures. We perturbed the word percentage, so with that represents the ratio of perturbed words to total text length. The accuracy results, original prediction accuracy. The report includes the accuracy of 3 targeted models on original test data. The prediction accuracy under adversarial attacks, and then we evaluate the target model's accuracy under adversarial attacks. So before we attack it, we measure the accuracy, it's usually high. After we attack the model, the accuracy goes down. We compare with the original accuracy to determine the efficacy for adversarial attacks. Larger disparity indicates higher effectiveness of adversarial attacks. The attack model efficiency we measured by the number of queries made by text attack framework to retrieve corresponding predicted probability scores. So for the data sets and algorithms, again, we use the in-round spam, SMS spam collection, link spam, and these are widely recognized and essential for evaluating spam detection models. Again, the algorithms were Roberta, Baird, and Synergy. These are state-of-the-art algorithms used for exceptional performance in spam classification. The rationale behind the model selection choice again of Roberta, Baird, and Synergy for the spam detection test aimed at ensuring first, diversity in model architectures and training paradigms, adaptability to spam detection, which is our task, ensuring comprehensive evaluation, and then these are state-of-the-art benchmarking models and datasets. So we had the model-specific adjustments, we had a feedback loop, we had the cross-validation, exploratory data analysis, we did that. We did the literature view, we did the regularization technique, and automated hyperparameter search, adversarial considerations, and optimization choices. For the evaluation metrics, we used classification accuracy, which quantifies the ratio of correct predictions to the total number of predictions. And then it provides a reliable measure of the model's performance. So for the in-run data set, for the models, Roberta, Baird, Synergy, the accuracy was 88.45 and then 91.67 and 78.32. For the SMS spam, for Roberta, the accuracy was 87.87. For Baird, it was 89.12. For Synergy, it was 75.88. For the link spam, Roberta was 89.12. For Baird, it was 90.57. And for Synergy, it was 81.98. So these are the results of the classification accuracy without adversarial attacks, before attacking the model. Now, under adversarial attacks, we can see that the accuracy has gone down significantly from 80s and 90s to 15, 12, 11, and then all the way down to 5.22. None of the models achieved high accuracy rates under adversarial attacks, which indicates difficulty in classifying spam instances in these datasets. And then for general insights, adversarial training improves model performance because for the in-run data set, we can see that the accuracy went up. Further analysis and experimentation can provide deeper insights into model's strengths, weaknesses, and potential areas for improvement. And here are the results again. Classification accuracy under adversarial attacks after model retraining, you can see it has gone down. We have 19.87, 22, 18, 13, 17, 12. The classification accuracy significantly declines after models are subjected or experience adversarial attacks and subsequently retrained. BERT consistently outperforms other models across various datasets. Performance variation. Adversarially trained models show different performance levels when switching from sentiment analysis to spam detection. For example, with sentiment analysis for BERT, MR, and Yelp, the accuracy was 15.75 and then 19.88. For spam detection, the accuracy was higher, 21.65 and 16, and then 16.65 for link spam. So we examined the influence of out-of-distribution data on adversarial training performance across different tests. So again, this shows the evaluation metrics and the comparative results. MR dataset, Yelp, SMS, spam, link spam, etc. Adversarial attack. So we know that out-of-distribution data negatively impacts adversarial training performance in NLP models. The impact varies slightly depending on the specific learning task, whether it's a sentiment analysis or spam detection. Generally lower accuracy in classifying instances when faced with adversarial examples. Accuracy values indicate challenges in handling adversarial attacks across different data sets. The role of OOD data crucial in shaping the efficacy of adversarial training in NLP models. Adversarial training again is a valuable method for improving model accuracy and resilience to adversarial perturbations. So some of the key insights of adversarial training is a promising direction for enhancing model robustness in spam detection. Temporal effects crucial to consider as models encounter new data sets and operational realities. Adversarial training benefits again fortifies model resilience. Ongoing iterations, continuous iterations, and evaluations are essential to address real-world deployment challenges. For future research direction, explore the impact of training data shift and concept drift of NLP models in real-world scenarios. Generalizability and applicability aim to understand how findings apply across different linguistic tasks and domains. Potential solutions would be both simple and sophisticated techniques to enhance model robustness and adaptability. And this is the end of the presentation. Thank you.